I will begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you for this class and the students. Just ask you to guide our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get straight to it. So here we have x, y prime equals to 3 minus 2, 2, 3, xy. So identify the matrix of the problem here. A is this 2 by 2 matrix. So I get to work on it. I need to calculate the eigenvalues of A. So I take the determinant of A minus lambda I, which is the determinant of 3 minus lambda minus 2, 2, and 3 minus lambda. That gives me lambda minus 3 quantity squared plus 4. All right, so if I look at this and I set this equal to 0, this means that I have lambda equals to 3 plus or minus 2i. So I have a complex eigenvalue for this problem. So this is a 2 by 2 system, right? You might add a date to the top one. Right. This is a 2 by 2 system, which means we're looking for two solutions, right? Two fundamental real solutions. And so remember last time I told you every complex eigenvector gives you two real solutions, which means that we just need one complex eigenvector. So you can either choose the plus or the minus, but make a choice. I usually choose plus. So let us set lambda equal to 3 plus 2i. I'll return to why this choice doesn't actually matter. All right? In terms of as long as you stick with it, you'll get the right answer. All right, so here we go. So I have A minus 3 plus 2i times the identity matrix times the vector I'm looking for, let's call it u1, equals to 0. I need to solve this equation. All right, so this is, I'll write it out in detail, 3 minus 2, 2, 3, minus, and I'll actually write the matrix out this time since it's a little bit tricky. So we've got 3 plus 2i here, 0, 0, 3 plus 2i. All right, so we need to subtract these two 2 by 2 matrices, and we're looking for the solutions of this system. The solution, the non-zero solution of this system will be a complex eigenvector. All right, so great. This is going to give me what? I get 3 minus 3, so I get a minus 2i and minus 2, 2, and down here the 3's, they be canceling. And I get a, looks like a minus 2i, right? uv equal to 0, 0. Now what's the deal? Are we supposed to get a unique solution, or are we supposed to get infinitely many? You know we're supposed to get infinitely many, right? Otherwise it wouldn't be an eigenvector problem. If we have a unique solution, then we'd have to have 0, right? So it should be the case, if we did our math right, that the one equation is simply a multiple of the other. And I think maybe you can see that if you take this right here, right, and you multiply by, minus I, right? What would that give you? That would give you minus 2i u, right? Well, anyway, let me not write it out. That is the second equation, right? Because I get the minus 2i here, and notice that like minus 2 I times minus I is what? 2i squared, but 2i squared is minus 2, right? Which just, this is not helping us solve the problem. This is just a check on our calculations, right? If we did this right, it should be the case that one of the rows and the other row are just multiples of one another. But it's usually going to be a complex multiple, so it's not always readily apparent in these problems. I'm just saying, to check our work, we should check on that. Now, if you want to live dangerously, you can just skip this check and go on. See, because logically, it doesn't matter. Either one you could pick and solve, because they're the same equation. that has to happen if we did our math right. So I like the second equation because it gives me 2u minus 2iv equals to 0, which gives me that u is equal to iv. All right? So then you can make u whatever you like. And u and v should be understood to be complex values here. So if somehow you got division by a complex number, make u or v such that you get rid of that division, you know? But here we should probably just put v equal to what? What do you guys want to do? V equal to what? 1. I like that. Good choice. And so, I mean, any other choice would be wrong, right? I mean, not really. It would just give us it would just give me a different looking solution, but it is in fact logically the same amount of, let's say, intellectual capital. I don't know. Let me get rid of this error check as it serves no purpose.
Why is u equal to negative I and not just I? If u equals iv and v equals 1.
Oh, did I put minus? Oh man, that's not a good sign. Thank you. So, yeah, I'm thinking about asking to not teach at 8:15 in future semesters. I may give up teaching the courses I like. I may just be like, I don't care, I'll teach college algebra, whatever, just don't put me at 8:15 again. It's like, it's just bad. Anyway, okay, so we have u1 equal to I1. There you go. That's my complex eigenvector with eigenvalue 3 plus 2i. Okay? And so just, you know, side note. So what we have now is we have a times u1, right, is equal to 3 plus 2i times u1, right? So do you guys know about the complex conjugate? What's the complex conjugate of an equation? So complex conjugation is when you switch I to minus I, right? So if I take the complex conjugate of this equation, what does it give me? Complex conjugate, complex conjugate. I get a complex conjugate times u1 complex conjugate equals to 3 plus 2i complex conjugate times u1 complex conjugate. Now, what is the complex conjugate of A? Here's A. What's the complex conjugate of this? It's what?
The same thing.
The same thing, right, because it's real, right? So a way you can define something being real is if it's equal to its own complex conjugate, right? So that's the case for the matrix. The matrix A is real, so A conjugate is just A. So what we have is A, u1 conjugate is equal to 3 minus 2i. That's the complex conjugate of 3 plus 2i times u1 complex conjugate. So what this little calculation down in the corner shows you is that if we had, instead of picking 3 plus 2i, if we'd picked 3 minus 2i, then the answer, the eigenvectors to the complex conjugate eigenvalue, are simply the complex conjugate of our eigenvectors that we found. All right, but we're going to see in the next step to the solution process that it's really the same solution, just kind of repackaged a bit. So in short, we don't need this stuff in the corner. It's just a comment. It's not really part of the solution. It's just a, you know, here's why we don't care about that, because there's nothing new there. All right. So 3 plus 2i's got everything we need. So let's put it all together. So we get complex solution z, I'll call it z vector, equal to e to the lambda t times the, you know, u1 vector, which in particular here is e to the, what was it? 3 plus 2i times t, right, times u1, which is e to the 3t times, well, the way that works out by definition is cosine 2t plus I times the sine of 2t. So you need to learn this if you don't know it already. And the u1 we'll write as a1 plus I times b1. So here, u1 we said was I1. We can rewrite that as 0, 1 plus I times 1, 0. So to be explicit, and it saves us to not be explicit for a bit here, but this is what I mean by A1 and this is B1. So this is the standard notation which I believe is used in section 9.6 in your textbook, for example. All right. But rather than just copying down for you like a recipe for how to just write down the solution, I'm showing you how to derive it from base principles, okay? Okay, so this is a complex solution. Last time I argued that every complex solution gives us a pair of real solutions. So multiply this out, what do you get? We've got what? We've got e to the 3t. And then we've got ourselves a cosine of 2t a1. And then I times I is minus 1, so we get minus sine of 2t b1 plus I times e to the 3t. And here we get cosine of 2t b1 plus the sine of 2t a1. So let me just write down what this is explicitly, okay? So like, what are we looking at here? What's this all together? Let's put it all together. This is e to the 3t, right? Times what? A1 is 0, 1, right? So this puts a cosine t here, cosine 2t, right? And b1 is 1, 0, so that puts a minus sine 2t here when you work it out, right? What I just wrote in blue there, that's the real part of the complex solution. On the other hand, this over here gives me e to the 3t times what? Times cosine 2t and sine 2t. So the I is not part of that. This is the real part of z. And this over here is the imaginary part of z. And the general real solution is going to be a linear combination of these two things. All right, so I can solve dr dt. Well, let me just give it a name. Star. Okay, we can solve star with x comma y, xy here, equals to c1 e to the 3t minus sine 2t cosine 2t plus c2 e to the 3t cos 2t sine 2t. All right? And there you go. That's the solution to this system. That's how you do it. What's the difference between this and the real case? What if I have a 2 by 2 system which has two distinct real eigenvectors? I mean, two distinct real eigenvalues. How does that problem differ from the one we're looking at here? Nobody?
We don't end up with trig functions.
Yeah, we don't end up with trig functions. That's a very good comment. Yeah, for sure.
What was the question again?
what's the difference between this kind of example and a 2x2 problem where we have, say, eigenvalue 3 and 7, like real eigenvalues? So here's a difference for the, yeah? Okay, let's see. So for like the real case, we only get one solution from each eigenvector, right? So if you got a 2x2 case and you got two distinct eigenvalues, you're going to have to solve the eigenvector problem for the one eigenvalue. That gives you one vector. You have to solve the eigenvector problem for another value. That gives you another vector. And then the solution is like c1 e to the lambda 1 u1 plus c2 e to the lambda t u2. But their lambda 1 and lambda 2 are just real, right? So you don't have to do this real imaginary part thing, right? There are no sines and cosines, they're just exponentials, but you're also burdened with the problem of finding two eigenvectors. This, on the other hand, you have to find one complex eigenvector, but then you end up using the real and imaginary parts, right? So like the takeaway message here, the theorem is just this, right? If you have a u equals to lambda u for u equals to a plus a vector plus ib vector, a and b being real vectors, and lambda equals to alpha plus I beta, then you obtain x, let's say r1, equals to e to the alpha t cos beta t a vector minus sine beta t b vector, and r2 equal to e to the alpha t sine beta t a vector plus cos beta t b vector, real solutions of dr dt equals to ar. And that's it. Each complex eigenvector gives us two real solutions, which we obtain by taking the real and imaginary parts of the complex eigensolution, which is this here, right? E to the lambda tu. So two real solutions from each complex solution. Question? No. Okay. That's it for the complex case. Now, we can also talk about generalized complex eigenvectors, right? And the same story goes through there. If you have a generalized complex eigenvector, right, you take the real and imaginary part of that kind of solution, and it will again give you two real solutions. Like you guys just told me, it's going to have sines and cosines in it generally. Whereas if you look at the generalized eigenvector solutions like we did last time, or the time before, those don't have sines and cosines, right? They just got exponentials. But they can also get a multiplication by t or t squared if you happen to have like a generalized eigenvector of order 3. Yeah. So there's a few things to sort through here, but I think you'll put it all together as you finish working out the homework and look at the notes and everything settles. So that's it for the homogeneous problem. Yep.
So when you were saying that you have like two different solutions for one eigenvector, would part of that be because you get lambda minus 3 twice, sort of like how it was on the quiz? Or
Oh no, there's just one complex eigenvalue of 3 plus 2i here. There's no two lambdas.
well, no, because you get lambda minus 3 squared. So would that have nothing?
Oh no. This doesn't mean there's a repeated eigenvalue. No. This factors to lambda minus 3 plus 2i, lambda minus 3 minus 2i. So they're distinct eigenvalues. They just happen to be complex. It's fundamentally different than the repeated eigenvalue case. When you have a repeated eigenvalue for the 2x2 case, unless it's a diagonal matrix, it's going to be the case that we only have one real eigenvector, and then the other one has to be the generalized eigenvector of order 2. We have to use the matrix exponential to get the solution in that case. So it's different.
So it's like the reasoning is different from like on the quiz where it was.
Yeah. Yeah, the reasoning is different. Okay, yep.
For R2, is that supposed to say sine of beta t?
There you go. Now there's another fun fact I should share with you guys. And this is just a, well, a fun fact. So if dr/dt equals to AR has solution, let's say fundamental solution matrix, big X, right? So that's a 2 by, well, it could be, it's an n by n matrix of functions, right? Usually. Then the general solution is R equals to X times a constant vector. So that's a matrix column. So what's that saying? That's just like the matrix notation for saying you take a linear combination of the columns of your fundamental solution matrix. Now this isn't quite what's interesting yet. So this is, like, to be more explicit, what I'm saying is R of time t is equal to the fundamental solution matrix of time t times your vector of constants. So here the C would be like C1 Cn, all right? And then you can work out, like, okay, so great. What about initial conditions? Like, what if we have an initial condition? How does this formula work in that case? Well, if we have that R of time t naught is equal to R naught, so this is like a given initial condition, you know, and to be clear, it's an initial condition vector, so actually it would be n initial pieces of data, right? For like a 2 by 2 system, I need to be given like both the x and the y for a given time. But if that's the case, then we need to have R naught, right, is equal to x at time t naught, right, times the constant vector. So what's the constant vector going to be? So at this point, those of you who have had 221 or just are a little bit more comfortable with the matrix stuff, you maybe will tell me what to do at this point. I want to solve for C. How do I do it? X of t naught's a matrix. How do I solve for C? So I can multiply by the inverse matrix at time t naught, right? And when I do that, it cancels this guy, and we get that the constant vector is actually equal to the inverse matrix of the fundamental solution matrix at time t naught times the initial condition R naught. So therefore, here's the possibly useless formula. The general solution then, which is not a general solution anymore, the solution to the initial value problem is in fact given by x of t, big X of t, times the x of t naught inverse times your initial condition vector. And so there you go. That's a formula that your book derives somewhere in chapter 9. This is the formula to fit the initial condition R naught if you have a solution matrix X. All right. So let's look at how this looks for this example 1. All right. Like, can you tell me how to build a fundamental solution matrix for the problem in example 1? Like, what would X of t be? We can build X of t. It's a 2 by 2 matrix. So what we do is just put the e to the 3t into the solution here. And so, like, we'll have e to the 3t sine 2t? Can't read. Sine 2t. There's a minus here. e to the 3t cos 2t. All right. And e to the 3t cos t. E to the 3t sine 3t. Sine 2t rather. So there you go. This is the fundamental solution matrix for example 1. All right. Well, is it fundamental? Like, what does it take for a solution matrix to be fundamental? You guys remember? It has to have non-zero determinant. What's the determinant of this one? So I get what? I get a e to the 3t squared, right? There's a minus sine squared 2t, and then minus e to the 3t times e to the 3t, e to the 3t squared, cosine squared 2t, right? So if you work it out, looks like we just get minus e to the 6t is the determinant of the fundamental solution matrix here. Which of course is non-zero, right? Which shows you that the matrix is everywhere invertible, which speaks to the linear independence of the two solutions we found, right? They genuinely are independent solutions, which is good. All right. So, listen, this is this kind of scary, beastly thing in general here, because we're talking about finding the inverse of an n by n matrix of functions. That's a kind of horrible calculation. So you're like, how is this any use? Well, it's of use to you because I'll ask you not n by n problem probably. I'll ask you a 2 by 2 problem, in which case we have a formula for the inverse, right? What's the formula for a 2 by 2 matrix inverse? If I got A, B, C, D, what's the inverse for this? Yeah, we do AD minus BC. Flip the diagonals. Flip the diagonals. DA. Minus is on the off diagonals. So there you go. This is the formula for the 2 by 2 inverse. So like, I can straight calculate the inverse for this guy at time t would be what? So by the way, this down here in the denominator, what is that? Do you recognize what this formula is? What's this term right here? Yeah, that's the determinant of A, B, C, D. So we already calculated that for my solution matrix, right? So we have minus 1 over e to the 6t. And then I just have to do what? I have to flip the diagonals. So I've got e to the 3t sine 2t and minus e to the 3t sine 2t. Minus is on the off diagonals, so minus e to the 3t cos 2t. And minus e to the 3t cos 2t. Now let's simplify this because this is kind of a mess, right? So what's the inverse to the solution matrix here? We find x inverse of t is equal to, if we clean it up, bring the minus in, cancel the exponentials. In fact, what I'm going to do is I'm going to keep that exponential outside, if you guys don't mind. I'm going to put a 1 over e to the 3t out here because that's really what we've got, right? So like 1 over e to the 3t, and then I've got a minus sine 2t minus cos 2t cos 2t and sine 2t. So I think I got to correct the signs, the plus minus. Let me take a step back here. So I had minus, 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 which I was trying to cancel with the minus over here. So I should have plus on 3 terms and minus on 1. There we go. So that is a formula for the inverse of the fundamental solution matrix here. And if I wanted to solve example 1, right? So like if we have like r at time 0 is equal to say x naught, y naught, I mean y naught, right? Then we can say r of t is equal to what? Well, general solution, I do x of t times x of t of time 0 inverse times this x naught, y naught. And we could work that out, right? And that would give us the formula for the solution that goes through x naught, y naught. And we wouldn't have to solve a system of equations. Like writing down the inverse formula for the 2x2 matrix, it does all that for us. What is this? What is x of 0 inverse, though? Can you see what that actually is? What happens when you put t equal to 0 into this? Again, what is x of 0 inverse? What happens when you put t equal to 0 into the formula up there? Sine is 0, right? Sine of 0 is 0. Cosine of 0 is 1. E to the 3, 0, 1. So we simply get the matrix 0, 1, 1, 0 in this particular instance. Yeah? So I can multiply this out, and that will give me straight up the solution to that initial value problem, right? I'm going to resist the urge to actually finish that calculation because we have something deeper to talk about here. All right, so what if we don't have a homogeneous problem, right? Like, what about the non-homogeneous problem? So what is that? Let's talk about that. I guess I'll carve myself out a over here. So if we're up against solving the problem dr dt equals to a times r plus f vector, this is the non-homogeneous problem. Right. So like, for instance, the way that would look over here, if I modify example 1 just a bit to make it non-homogeneous, all that means is like I'm adding a function to each one of the equations, right? So like, I just add some extra term like f1, which is possibly a function of time here, and f2, which is possibly a function of time there, right? Those two terms I group together to make the inhomogeneous vector. If that's non-zero at even one time, it's a non-homogeneous system, and we have to think about how to solve that. All right? So we want to find basically the theory says that solution R can be written as like the particular solution plus what's called the homogeneous solution. Now we've already talked about how to find the homogeneous solution. That's everything we've been doing. The homogeneous solution solves, you know, dr dt equals to AR. But the particular solution, we want it to actually solve the non-homogeneous problem. Okay? So what's the method? Like, how do you find a particular solution? Well, there's something called variation of parameters. So the technique is this. We suppose that R, the particular solution, can be written as the fundamental solution matrix X, all right, times some vector of unknown functions. the parameters. So this is the method variation of parameters. So the question is, what is this unknown function v? Like, how do you find it? So if this is going to be a solution to the non-homogeneous problem, what does it have to do? It has to solve the non-homogeneous equation. So what do? We take our guess and we try to plug it in up here and see what it has to do, right? So let's do it. We differentiate this. All right, so drp dt is equal to ddt of the fundamental solution matrix x times this vector of unknown functions that we're trying to figure out what it is, right? We're trying to find a condition on v so we can find it. All right. Now, of course, this could go horribly wrong, right? Just like, you know, maybe you're searching for a mate who, I usually give the example of like, they like, you know, Star Trek and Star Wars. You know, that may be too much. You may have to settle on, you know, just a fan of one of the genres and not both. But I don't know. I need to find new examples. Anyway, so these are both functions of time, right? So we have to do the product rule. The product rule here, which is dx dt times v vector plus x times dv vector dt. All right? Now, this is a fundamental solution matrix, right? As we talked about, fundamental solution matrix makes this equal to ax v, right? AXV. Because it's the fundamental solution matrix, so dx dt has to be equal to a times x. But on the other hand, we're assuming that dr dt equals to what? Equals to AR plus F, right? And so what is ARP plus F? Well, that's AX times V plus F. So let me point out, we've got this right here. It has to be equal that right there if my guess is going to work out. Oh, hey, look, stuff cancels. Woohoo! Right? Huzzah! Sorry. I'm an idiot. But this has to be equal to that. Can you solve that equation? So we desire, it would be desirable for us if we could solve the solution matrix x times dv dt equal to my vector of inhomogeneous terms. How do you solve that? Let's multiply by the inverse again, see? So we've got dv dt is equal to x inverse, the matrix inverse, times f. What is it? What?
I was just trying to figure something out.
Oh. All I'm doing, just to recap, I'm plugging the solution in to the differential equation, and I did the product rule, and then I put it at both left-hand side equal right-hand side. And when I do that, we end up canceling AXV from both sides, which just leaves us with x times the derivative of our unknown vector of functions dv dt equals to the given non-homogeneous term f, which I have up here. Then I multiply by the inverse matrix to isolate this. Now how do I solve for v? This takes us back to like the beginning of the course, right? What do? How do you isolate v here? Integrate, right. So this gives us v is equal to the integral of x inverse times f, let's say dt. And there you go. My particular solution is equal to x at time t, the integral of x inverse of t times f vector of t dt. And that right there, guys, is the formula for variation of parameters. Now, this is only helpful for us for like I can really only ask you 2 by 2 problems, because only in the 2 by 2 case do we actually have like nice formulas for the inverse, right? But we could actually carry this out. We could carry out this using the formula I have over here. See, like for this particular example, it would be, you know, e to the 3t times my, what was it? Oh, goodness gracious, I can't read. Minus sine 2t, cosine 2t, cosine 2t, sine 2t, integrate, and I have to integrate, you know, x inverse, so that's 1 over e to the 3t times that matrix minus sine 2t. I'll get out of the way here. Cos 2t. So all I'm doing, guys, is I'm writing down the formulas for the inverse fundamental solution matrix we derived over there for this example. And then you have to multiply by the matrix of functions f1, f2, and integrate that thing. And that is the particular solution. So if I was to assign this on like test 1, it'd probably be like a take-home problem, because we just don't have enough time to work through all of this in the end class. Unless I like majorly give you some kind of shortcuts, but it would be kind of forced. But it is something you should know about, because some problems are non-homogeneous, and this is how you solve them. Variation of parameters. There's another variation of parameters later in the course, which is for a single problem of nth order, and it turns out that that variation of parameters is far more complicated. It is one of the great ironies of this course to me, that you can derive variation of parameters for systems in like 5 minutes. And okay, yeah, it's ugly because you got to invert a matrix of functions and stuff, but this is a straightforward technique, albeit it is nevertheless an integral. All right, so that's that. So I think on your quiz 5, there's like one of these. So I wanted to give you, you know, a heads up. This is how you solve it. All right. Now, so there that is. There's that. So in the time that remains, everybody got it? Because I'm going to use the projector here. I'll give you a couple seconds to take a picture or whatever. The remaining bit here, well, there's a couple things. Number one, I should draw your attention to the fact that there are oodles of examples in the notes of like eigenvector problems. If you haven't noticed already, I made an announcement about this, but oh, make sure I can find the thing I'm looking for. Ah, come back to me, cursor. Curse the cursor. All right. Okay, cool. Got that. All right, so I won't really say, come on. Come to us. Well, sometime before class ends, please. I didn't realize I should have done this 3 minutes ago. Oh, there we go. So this is solutions by eigenvector. Like, see my notes. Come on, work. So I have some, you know, really simple, basic examples like this one, the 2 by 2, right? So, you know, I show you. We get that's our eigenvector. Choose u equal to 1 gives us this. Right, that's a transpose. This is a way of writing it as a column vector. So there's your solution. Solve the other eigenvector, right? Choose u equal to 1. There's your other solution. And then put together the general solution. Here it is, right? Yay. So we did problem like that in class. Next one is, oh, this is the only way you could have repeated eigenvalue in the 2 by 2 case and have enough eigenvectors if it's diagonal. That's like that. It's the only possibility. as it turns out from the math. And in that case, you get these two solutions, right? But otherwise, let's see here. So I want to skip ahead a bit. All right. So we've been doing this kind of stuff today, the complex case. This one here is a 3x3 with distinct real. We looked at an example like that. This one here has repeated eigenvalue of 2. And this one's a little bit different than anything we looked at in class so far. I would point out this example is interesting because you have a repeated eigenvalue of 2, and you end up with, let's see, where is it? You end up with this, right? So this is just one equation, which ends up meaning that there's two parameters in the solution. You get v is free, and you get w is equal to minus u. So you've got a u and a v in your solution. When this happens, you basically factor out the separate parameters separately. So you're like u times, you get a u times 1, 0, minus 1, and you get a v times 0, 1, 0. You get two linearly independent eigenvectors, and so I get two eigensolutions from this one. So the 2 gives me this and that. All right, so that is something we didn't come across in class, but that can happen. All right. So anyway, I just advertisement for my notes. There's more examples. I can only work so many in class, as you know. The other thing I wanted to talk to you about, and we'll talk more about this Friday, like the theory of it, but in a nutshell, the last problem in your team mission, problem 25, which I'm sure you're all have already tried, and you're like, we didn't cover this material. Well, that's true, sort of, but I'm changing that now. So in short, if we have a problem which is basically one-dimensional motion with a conservative force, in that context, energy is conserved. And so what you can do is you can make a plot of, so here G is basically potential energy. So I make a plot of potential energy here, and down here I make a plot of position and velocity. And the way this works is for different energy levels, like K1, K2, and K3, that gives me corresponding trajectories down here. And in short, when you work through the theory of it, any place there's a critical point of the potential, there ends up being a critical point in the phase plane down here. And the other big thing is energy is kinetic energy plus potential, right? So if you have an energy level, you can only have a solution when your total energy is above the potential energy. So like K1 is unphysical if I'm over here or over there, because I'd be below the potential energy, which is why I just get this circle for energy K1, and then this circle for energy K2, and that circle for energy K3. See, because for those energy levels past that, it would correspond to like negative kinetic energy, which we can't have. So in short, the method for example 25 is you just plot the potential energy and then kind of follow this example. You should be able to do it. Oh, come on, don't do that. There's another example. Come on. Where'd it go? I had two examples here. I thought I had two examples. Well, here's a more complicated one. So in these notes, G is the potential energy. So here, if this is my potential energy, then here's different energy levels. Like K1, it's only, the energy is above the potential only like here and here and here and here, which gives you these like loops. See, like that. And then up here, energy K4, it's never, you never have the total energy matching the potential energy, right? Which means that there's always some kinetic energy. This is velocity versus position. So what that means is the velocity is never 0 for energy K4, which is why you get this level here. So I hope these are enough for you to figure out problem 25. Just do your best. I'm sorry I didn't lecture on it better. I got stuck on that example the other day and it put us behind, basically, what happened. My apologies. But
This is on the website.
yeah, this is the announcement I made. I think I made an announcement about this, right? I know you guys don't read announcements always like right away, but it's there. Thanks, guys.